This is number 66B and number 68 in chapter 18. These two questions are related to one another. We have this redox reaction. We have gaseous oxygen and water, and solid copper is in redox equilibria with 4 hydroxides and 2 coppers that are +2. And so number 66B is asking us to solve for delta G. And then 68, which is a follow-up, is asking us to solve for K. So for our delta G, we really want to use this expression. We want to determine the cell potential at standard state. And once we have the cell potential at standard state, we can solve for delta G. So that requires writing down our half reactions. And so our oxidation half reaction would be the copper, where it's being oxidized and losing 2 electrons. And then the other process would really be your oxygen that's reacting to give you then 4 hydroxides. If we start to balance that process, right, that's where our 2 H2Os come from to balance out the oxygens we have on the right. And so now we're balanced with regard to atoms. What about electrons? The oxygen is going from a 0 oxidation number in O2 to a negative 2 oxidation state over on the right. And so since you're talking about each oxygen gaining 2 electrons in that process, right, we would have to have 4 electrons plus 2 waters plus oxygen gives us 4 hydroxides. So there is our half reaction for oxidation. There is our half reaction for reduction. And so in order to get the potential of the cell, we just want to take the difference of the reduction and oxidation half reaction potentials. And so if we look up our reduction potential, we get a value of 0.40 volts. And we're going to subtract off from that the potential we get from the table for the oxidation of copper, which is 0.34 volts. And so we get a value of 0.06 volts for the cell potential as written above. Now that we have our cell potential, we can solve for our delta G using our Nernst equation, which is going to be the negative of n, our number of electrons being transferred. And so in order to get the balanced reaction, right, we'd have to multiply the top by 2. So really there's 4 electrons being transferred overall in the process. We have our Faraday's constant of 96,500, and then we have our cell potential, which is 0.06 volts. And so if we solve for that, we get a value of negative 23,160 joules per mole, or negative 23.1 or 2 kilojoules per mole. So that's 66B, which is solving for our delta G of negative 23.2 kilojoules per mole. So we have a negative 23.2 kilojoules per mole for the delta G. Again, that's 66B. For 68, they're asking us to solve for K. And really we have 2 possible ways of doing this. We could solve for delta G and how that, relates to our K. Or we could look at how our cell potential relates to our K. You know, the cell potential is derived from the delta G expression, right? So either one of these equations will work and give you the same answer. I'm going to use the second one, the cell potential. And so if we plug in our values that we got from 66B, for instance, our cell potential, remember, we calculate it to be 0.06 volts. So that's what we're going to put in there. That's equal to that constant over our n. That's still going to be 4. And then we're trying to solve for that equilibrium constant, K. And so if we do some rearranging, we should get 4.054 is equal to that log of K. K then would be equal to 10 to the 4.054, or 1.132 times 10 to the 4th. And so that is our equilibrium constant, and that is the answer to number 68, which again uses some of the information that we found in 66B, which is why I included them together.